Recording in progress.
Okay, so welcome to this week's colloquium. We are very excited to have Raul Gomez visiting from a long distance and going to be talking about tempered distributions and differential equations on Nash manifolds. So thank you so much for being here. We look forward to your talk.
Okay, thank you. Thank you very much for the invitation. It's been a very nice week all along. I want to talk about these tempered distributions and differential equations on Nash manifolds. So just to clarify, I come from a background on representation theory. So the reason why I started working on this was to answer some representation theory problems, where I think that this approach might be of more like a general interest. So I will try to focus more on that part of the talk rather than on the representation theory part. I will talk about what are the problems that I was actually trying to solve, but that maybe that will be like not that relevant to everybody else. But in any case, let's get started. So for the outline of the talk, I first want to talk about what I mean by Schwartz functions on Nash manifolds, what are like tempered distributions and all of these things. So I will talk a little bit about semi-algebraic geometry, about Nash manifolds, Schwartz functions on Nash manifolds, and moderate growth representation. This is of course like related with representation theory. And then for the second part of the talk, I want to talk about some applications. The examples that I want to look at some very, very simple examples. So please be mindful of that. I mean, they will be like extremely simple, hopefully. If they are not simple, it means that I am not explaining myself correctly. So please ask questions in that case. So I want to talk about these gamma distributions. I want to do like some small examples with the group SL2R, and then talk a little bit about the problem that originated this idea, which is invariant trilinear forms on PGL2R. Okay. So let's start with Schwartz functions on Nash manifolds. So we will start this talk with the definition and basic properties of the space of Schwartz functions on Nash manifolds. So we will follow the general presentation given by Eisenberg-Gorevich, although some ideas can be found earlier in the work of Duclos. Here are like some of the references if you are interested in learning like this with more detail. And let's start with this very like well-known definition, right? And for R, for the real numbers, the definition of the Schwartz space is given in this form. So I want a function that is smooth, and I want my function and all its derivatives to be rapidly decreasing. What does that mean? It means that every time that I multiply by any polynomial, I still want my function to be bound. So the goal of this section is to extend these definitions to more general classes of spaces. I want to have it not only for the real numbers or for like Rn. And we observe that the above definition depends on being able to define polynomial functions on R. So it is natural to restrict our attention to spaces with some sort of algebraic structure, right? If we have like some kind of like general, like regular function kind of thing, then we can try to like generalize this definition. So semi-algebraic geometry appears as a natural framework here. So let me talk a little bit about this semi-algebraic geometry. So a subset X of the Rn is called semi-algebraic if it can be presented as a finite union of sets defined by a finite number of polynomial equalities and inequalities, right? So the key word here is finite. So for example, I can take this set, right, like the standard open board. That's going to be a semi-algebraic set. And one thing that is important is that, remember, I want to be able to write it as a finite union of these guys. Right? If I already have my basic opens, then of course, like any open sets, like it's smooth or analytic or whatever, I can just cover it with these guys with an infinite number of these guys, and I will get exactly the same sets. But those are not what I want. I want to be able to cover it with a finite number of these guys. So that's the key difference. So another example is, for example, like the positive real line, and I want to see it as the projection of this parabola. So I have the equation y equals to x squared. I project over the y-axis, and then I no longer get all the real numbers. I only get the positive ones. But I said that inequalities were okay, so I'm fine. This is still a semi-algebraic set. Okay. So the reason why we want to include inequalities in semi-algebraic geometry is precisely because I want the projections of semi-algebraic sets to be semi-algebraic so that we have a nice category. Okay. So let's take two semi-algebraic sets. We say that a function is semi-algebraic if its graph is a semi-algebraic subset of the cross product. So for example, I can take this function, right? I can take 1 plus x squared. This is always positive, so I can take the square root. So in this case, the graph of this function is going to be precisely, well, I have the equation y squared minus x squared equal to 1, but I am taking only one branch. So I want my y to be greater or equal than 0. But inequalities are okay. So this is a semi-algebraic function. So as you can see, like in semi-algebraic geometry, I have like the usual polynomial functions, where I can also have like solutions to algebraic equations. So it's a little bit more flexible than that. Okay. So semi-algebraic map satisfies the following property, and they have like some very nice properties. So the first one is that the image of a semi-algebraic subset of Rn under a semi-algebraic map is semi-algebraic. Remember, as I said, for this, it was important to have these inequalities. Otherwise, the example of the parabola will be a counterexample. But we have seen that now, that effectively is semi-algebraic. The second property is that if you take the closure, like the standard closure of a semi-algebraic set, it is still going to be semi-algebraic. The composition of semi-algebraic functions is semi-algebraic, so we indeed have a category. Finally, when you take R-valued functions on a semi-algebraic set X, they form a ring. And if you have a function that is nowhere vanishing, then this function is invertible in this ring. In other words, if I have a semi-algebraic function that is nowhere vanishing, then I can take the inverse of that function, and that's still going to be semi-algebraic. And finally, we have this condition, and this is the important condition when we want to define these Schwarz space and temporal distributions. If I have a semi-algebraic subset of Rn, and if I have an R-value semi-algebraic function, then there exists a polynomial function in n variables such that the value of my function is bound by this polynomial guy. So essentially, like the new function that I am introducing, I mean, I'm introducing more functions, but the growth of this function is controlled by polynomial functions. Okay, so now let's talk about Nash manifolds. So a Nash manifold is a semi-algebraic subset of Rn, which is a smooth manifold. So I want it to be semi-algebraic and smooth. So if I have U and V open semi-algebraic subsets, then a function from U to V is said to be Nash if it is smooth and it is also semi-algebraic. So in other words, we want to combine like the best of two worlds, right? We want the smooth world, we want the algebraic world, and we want them to interact nicely. So as a remark is that the inverse function theorem holds for maps between Nash manifolds. So I will have like this equivalent, which means that I can solve like this kind of like implicit function theorems, like all of these kind of results. They are valid in this category with when I have Nash manifolds, when I have Nash functions, sorry. And the second one is that the set of open semi-algebraic sets do not form a topology, right? And this is an important point like to keep in mind. But remember, like these semi-algebraic sets, they have to be finite union of like sets defined by these polynomial equations. So I cannot take infinite unions because again, I mean, if I do that, then any open set will be semi-algebraic, and then what is the point, right? And that's definitely not what I want. So I have to be careful here because I want to define some rings of functions, and I want to say that they form chiefs and co-chiefs and all of these things. And it says, well, you don't have a topology. Okay, I'm going to take the corresponding Grothendieck topology. The other thing that I need to do is say, what do I call a cover on my set? Well, a cover is going to be a bunch of open semi-algebraic sets, but I cannot have infinite covers. All my covers have to be finite. And as long as my covers are finite, then I am okay. So I can do like, I'm going to be calling it like the restricted topology. Is essentially I have these open sets. I can take finite intersection. I can take finite unions. If I take infinite unions as we are used to, then I am outside my category. That does not work. Okay, so we have this theorem. It says that if I have a smooth manifold, it admits a Nash manifold structure if and only if it is diffeomorphic to the interior of some compact smooth manifold, possibly with boundary. And this means that generally, this Nash manifold condition, I mean, is not as restrictive as it might seem at the beginning. Right? Like essentially, like most manifolds we're going to be working with can be given this Nash manifold structure. The most notable example is like the surface of infinite gens, right? I mean, you will just have like something like this, right? If you have something like this, right, it just goes on and on and on forever. This has a manifold structure. This cannot be given a Nash manifold structure. And again, once again, like the problem is that if you could have like infinite, like union of an infinite number of open sets, it will be okay, but you do not have that. Okay. Let's talk about some like very basic definitions. I mean, the point that I want to make here is like the usual construction that we do in geometry can be like written in this language of Nash manifolds. So a Nash bundle over X, I will just have this tuple where I have a projection, I have a surjective map, and I want that each fiber should be Nash diffeomorphic to the standard fiber, which is Z. I want it to be semi-algebraically locally trivial. So what this means is I want to find a finite cover. Once again, like the keyword here is finite. And I want that over there, my bundle has to be trivial. So one thing to keep in mind is that these open sets, like this finite cover, I am not saying that on these open sets, it is just like the regular open. No, it could be like this open semi-algebraic set, and on there like have these trivial guys. So that's the thing to keep in mind, right? Like usually, like in geometry, we take like this differential geometry, and we just did observe to these open balls, right? Because we can always just cover with an infinite number of guys. Here, we don't really have this option, so we usually have to like take chunks of my space that are not precisely open balls. We are going to be okay with that. Okay, and here I will just explain more carefully, essentially what I just said. And there exists a semi-algebraic open cover. As you can see here, I want this cover to be finite. It goes from k equals to 1 to m. And I want this isomorphism that says that the inverse image of this open set should be my open set cross product with my fiber. Okay, so let's take X to be a Nash manifold. A Nash vector bundle E over X, well, it's going to be a Nash bundle such that with linear fibers and such that the trivialization maps are fireworks linear. Right, so this is exactly the same definition as vector bundle in like the differential geometry setting. And if I have a Nash manifold and I have a Nash bundle over X, a Nash section is simply a section on E. I just want my map to be Nash, right? And we have already defined what that means. It just means that when I look at the graph of this function, it should give me a semi-algebraic set. Okay. And then we have this proposition, like pretty much all the constructions that we do in differential geometry. We have the tangent, normal, conormal, densities, differential forms, etc., etc. You just write down the equations, you realize that if everything was semi-algebraic, then when I do these constructions, I'm still in the semi-algebraic setting. So everything just goes through. Okay. So given a Nash manifold, let X be a Nash manifold. A Nash vector field is going to be a Nash section of the tangent bundle of X. And we define the algebra of Nash differential operators on X to be the subalgebra of these like homomorphisms from smooth functions that are generated by Nash functions and by derivations along Nash vector fields. Right? So essentially, I will just take like these Nash vector fields, and the coefficients I just multiply by Nash functions. And any derivation, any Nash derivation sends not only smooth functions to smooth functions, but actually Nash functions to Nash functions. Okay. So once we have done like all of this construction, like check that pretty much everything that we wanted to do in differential geometry can pretty much be translated to this setting, then I can define what I mean by Schwarz functions on a Nash manifold. So let X be a Nash manifold. We define the space of Schwarz functions on X to be all the functions that are smooth. Remember, we want to combine the best of two worlds. And I want that every time that I apply a Nash differential operator, then this function is bound. Right? So it's pretty much like the same definition as in the Schwarz space. And you can check that if you apply this definition to the real numbers, then of course you should get like the same definition. Okay. And we have this proposition that if X is a Nash manifold, then the Schwarz functions on X is a Frechet space. And the Frechet space structure is just pretty much given by, okay, you take like this Nash, you take these Nash differential operators. I mean, you make sure that you take just a countable one of them. And then you take the absolute value of that. And you can, so what this is saying is that it suffices to take only countably many of those guys, right? Essentially, just the regular functions, for example, or the equivalence of those. Okay. So let X be a Nash manifold. A function, a smooth function f, is said to be of moderate growth if for any Nash differential operator there exists a Nash function that bounds it. Right? So essentially, I want my function and all its derivatives to have at most polynomial growth. And we will denote the set of moderate growth function by t of x. T, the idea is it comes from temper, so I want to think of this as temper functions. They are growing, but not out of control. And we have this lemma that if X is a Nash manifold, then the assignment, I have an open set. I assign the temper functions on this set. This defines achieve in the restricted topology on X. So remember what this means is that, okay, I don't have a topology. I can only take like finite covers. But with respect to finite covers, like all the usual properties of chips are satisfied. Okay. One last thing that I want to say about like this Nash this semi-algebraic theory is that you do have partition of unity. Once again, you have to be careful. I have this finite open cover of my set X, or my semi-algebraic set, and I will always have these temper functions, right, that are subordinated to my partition, and that they add up to 1. And besides, every time I have a Schwarz functions on my whole space, then I can use these guys to restrict it to Schwarz functions on my open set. So what this says is that temper functions have achieved structures. Schwarz functions have a co-achieved structure, right? In this case, I mean, we can like the big one, right? Like Schwarz functions on X can be written as sum of Schwarz functions on these small open sets by just using partitions of unity. Okay. Finally, we want to say something about like how to identify these spaces of Schwarz functions. Of course, I mean, we have our definition, but of course, it is not like such an easy definition to like work with. But we have the following properties. If X is a compact Nash manifold, then Schwarz functions on X are just smooth functions on X. Every single function is going to be bounded because, I mean, well, my set is compact, so it cannot go like too far away. The second one that is a little bit more interesting. Let's imagine that I have a Nash submanifold. I want this Nash submanifold to be closed, and I take its complement. Then the Schwarz functions on U are going to be precisely all the Nash functions on X, such that my functions and all its derivatives vanish on this set. So this is a very easy way to identify when I have like a Nash function. Essentially, if I have a function defined, I have a compact manifold, or I have a compactification of my manifold, and then I want to say, what are my Nash functions on a given open set? Well, look at the boundary, and what you want is I want my function and all its derivatives to vanish there, and as long as that happens, then you are good to go. And finally, we have Borel's lemma, which tells me that if this Nash manifold Z, this closed Nash manifold, has codimension M in X, then when I take the quotient of the Schwarz functions on X by the Schwarz functions on the open set, I get something, right, that is essentially Schwarz functions on Z, and then I take arbitrary derivatives. Essentially, I take Taylor series with respect to my transverse directions. And this is precisely what I get. So let's do a very concrete example. So I take X to be the real numbers. My closed set is 0, the origin. So in that case, Schwarz functions on R star are all the functions so that my function and all its derivatives vanish at the origin. And then what is the quotient? What is my SZ of X? Well, I just take my function and I just take the Taylor series expansion, and that's it. That's my quotient. It just looks like this power series on my variable x. So finally, just some comments, especially for people in representation theory. So if I have a real algebraic group, it will have naturally a Nash manifold structure. I have V to be a locally convex topological vector space. We say that the representation of G is of moderate growth if for every seminorm Q and V, it is going to be this other seminorm Q tilde, and a temper function on G, such that this happens. So if you notice, essentially what I want to say is I want my matrix coefficients to be bounded by some temper distribution, temper function on my group. And as long as that happens, then I am okay. A couple of remarks, final remarks here. So if I have a representation of moderate growth, then it will have a natural structure as an SG module over convolution, as I said the other way. This SG is going to be the space of Schwarz densities on my group. Right? So I will take a density on my group, and then this will have an algebra structure under convolution, right? So the usual convolution of like essentially of measures. In this case, densities, I want it to be essentially like Lebesgue measure times a short function. I can take convolution of that. You will have an algebra structure. Since these functions are Schwarz and my functions are moderate growth, then they will act on these matrix coefficients. Essentially, they will act on my representation. And the other thing is that if G is reductive, then Kasseman-Wallach gave a definition of what it means to representation to V of moderate growth. And of course, this definition is equivalent, right? So we're not like getting anything new in that sense. But if we have like other types of groups, like parabolic, nilpotents, et cetera, we can just apply these same definitions.
Can I ask a question about something on the previous slide, actually?
Sure. Here.
Yeah, why is there no growth condition on the power series you get?
The power series. No, so the thing is like this is the quotient, right? This is the result of the quotient. So I have the real line, but I am removing the origin. So what I have is functions that vanish, like the function that all the derivatives vanish here. I have like all my regular functions, and then I take the quotient.
Yeah.
And I say, okay, what is the quotient? How does the quotient look like?
Right, but guys, I'm confused. Why is it not surjective onto C double brackets X? Like,
Yeah, that's what it's lemma.
that's where I was. Okay.
Yeah, right. So this is like this is free, and that's not obvious.
So you're telling me if I do some more analysis.
Yeah. So it is not clear that if you have a Schwarz function, then and you take like an arbitrary power series that does not converge like at all, it is not clear that you can find a smooth function that really goes like here, that has like that as the Taylor series function. But what I showed is that is indeed the case. And that tells me that these quotients actually become like very easy to understand, because then you just take power series. Essentially, you just take Taylor series at the point, and you're good to go.
Well, thank you.
Yeah.
You should write on the table board so you on the screen.
Oh.
That's hard.
Okay. Thank you. I'll keep it in mind. Okay. So now let me talk about this gamma distribution. So as I say, like these computations should be straightforward. So if they are not, please ask questions. So the gamma function is defined in this way, right? So I take like e to the minus x, I multiply by this polynomial, and it depends on z, and then I just integrate over. And we know that if the real part of z is greater than 0, then this is absolutely convergent, so you just integrate. And we also know that E satisfies this functional equation. And using this functional equation, we can extend it to the whole complex plane. It's going to be a meromorphic function. Okay, so using this equation, we can extend it to a meromorphic function on the whole of the complex plane. Okay. So in this part of the talk, we will consider the following problem of meromorphic continuation. So what I'm going to do is I'm going to look at these functions. So I'm going to take the absolute value of x raised to the nu minus 1 power, and nu is a complex number. And then I'm going to take any Schwarz functions on R, and I'm going to take this integral. So essentially, I'm just multiplying by this guy. And the observation here is that as long as the real part of mu is greater than 0, this integral is absolutely convergent, so I have no problems. So what I would like to do is to extend this to a meromorphic function in all the plane. So let me be a little bit more careful. So we want to extend this to a meromorphic distribution on the whole of the complex plane. And what that means is that every time that I have a short function on R, I want this function that goes from nu to this integral to be meromorphic. Okay. So how do I do that? So the first thing to notice is that this distribution, right, this absolute value of x to the nu minus 1 is actually a solution to this differential equation. So I have d, it is this guy over here. Right? So you just try to find solutions to this operator, then you get this. And the second one is that this kind of problems, I mean, of course, is not new. It has already done before. In particular, Bernstein gave a vast generalization of this kind of results in this paper. But as I said, I just wanted to show a little bit like how it is done in this semi-algebraic setting. Okay. So what I'm going to do is the following. I'm going to take V, my space V, to be all the short functions on R. I'm going to take U to be the short functions on R star. And I'm going to take W to be the quotient of these guys. So I am essentially in the picture that is out of my over there. So I will follow Robin's suggestion, and I will just make the picture here. Right, so essentially, I will have like functions on the whole short space, functions that vanish up to all degree over here, and then the quotient they essentially looks like Taylor series around the origin. Okay. Notice that the dual of that space, what is the dual of that space? That's going to be temper distribution that are supported at the origin. So what we want to know is, we want to know what are like all the invariant distributions on this short space that are invariant under this differential operator. And how do I do it? Well, I break my space into pieces. I will have this open set, and I will have this closed set, and I am breaking it into these three spaces. So I want to analyze what happens in U, what happens on W, and from that, I want to put information together and know what happens on V. Okay. So what I want to do is, okay, I want to understand what is, our goal now is to reduce the problem of describing this space like the the invariant temper distributions on R by looking at U prime of D, W prime over D, W per D prime. So let's start by analyzing like these two spaces. So the first thing to notice is that if I have a function that is Schwarz over here, then this integral is always going to converge. So you remember the property of these Schwarz functions is that every time that you multiply by a function that has like moderate growth, my function remains bound. So it doesn't matter what nu is. If my function is Schwarz on R star, this always going to converge. So I don't have any problem. I just integrate it. So I will have this guy, I will have the solution. Okay. So from this, we have this thing. I should point out, this is not quite correct. You could have one over here, like one piece over here and one piece over there. The only thing is that I wanted to extend this to actually do solutions on some line bundle on the projective line, and I forgot to take that into account. We will see it later, right? That there is a way of seeing this as a solution of some twisted differential operators on the projective line. So yes, sorry about that. In any case, let me analyze this guy. And now what I want to do is, what are the invariant temper distributions supported at the origin? Well, I mean, I just have power series on the origin, right? So I just need to like check, what do I do with these power series guys? Okay. So essentially, as we mentioned before, this space corresponds to the space of all the solutions to the equation dt equal to 0, such that the support of my distribution is contained in the origin. Okay. And from this observation, we notice that, well, we will always have the delta distribution, right? Because I am multiplying by x, so that will always kill it. And I also have this other operator, which is taking k derivatives of the delta distribution, but this only works when k is equal to minus nu plus 1, when this is a positive integer, right? So in that case, I just apply my differential operator to my polynomial, I will kill it, and I will get another solution. Okay, so finally, I want to look at these W invariant elements of W and take this dual. And we notice, I mean, essentially, I just have to like understand what W over D is, and then I just dualize, of course. So we start by remarking, I mean, we have said that these natural projections from V to W can be identified with the process of computing the Taylor series expansion of the function f around the origin. So in other words, like this space W is just going to be power series in X, right? Coefficients completely arbitrary. So when I write down my equation, I realized that the only solution that I could have is going to be polynomials to a given power, and this only works when my k is equal to minus nu plus 1 is a positive integer. So as you notice, like essentially I have my integral over here, and what I want to say is, okay, if my function is rapidly decreasing at 0, then I can always integrate. Now, when I want to extend that to my whole space, then I might have issues. And the thing is that I might have issues precisely when I get extra distributions at 0. So essentially what I'm saying is that I have this distribution, and this distribution is meromorphic. So of course, if I have a pole, I can just resolve the pole, and I'm going to be getting new distributions. Right? So what this theorem is telling me is that, yeah, there is like a candidate of what will it be like if you resolve the pole, right? If your distribution happens to have a pole there, what is the candidate of resolving this pole? And it will be these extra derivatives, like these extra derivatives of the delta function at the origin. Okay, so now we want to combine this information, right? I have information about U, I have information about W, and I want to combine it to get information about V. And the technique to doing that is do some homological algebra. So I take this exact sequence and I dualize. And when I dualize, this sequence is going to remain exact. And then I'm going to take invariant functional. So again, I'm a little bit sloppy here. When I take like this first homology, like essentially what I am doing is I am looking at D as a one-dimensional Lie algebra. Then I am taking invariance with respect to that guy. And I am taking Lie algebra homology. And that gives me this long exact sequence. So this gives me information about how to put together B prime of D with information of W prime of D, U prime of D, and this connected map between U prime of D and the first cohomology. Now, it just happens that the first cohomology is precisely the invariant vectors in W, and then you take the dual, right? So that's why we were calculating this guy before. So essentially, we have like all the pieces that we need. The only thing that is missing is what is the connecting homomorphism from one to the other. So I have this long exact sequence, and my connecting homomorphism is precisely like taking the derivative, right? So I am taking like these invariant distributions, and essentially what I want to do is the following. So I take this guy, right, like this integral, and I take a function such that when I apply my operator D, my function and all its derivatives vanish at the origin. But that does not mean that it will vanish outside the origin. So if it doesn't since it doesn't vanish, then I can apply this guy. Right? If this guy is equal to 0, then that means that it's okay. I can extend my distribution to the whole of the short space. But if this guy is non-zero, then I have problems, right? I will have an approach. Okay. So this is my theorem. My distribution J nu is going to extend to the whole of V, to the whole of my short space, if and only if every time I have a guy in W over D, and I perform this calculation, I get 0. Okay. So using this theorem, we can finally solve the problem we started at the beginning of this section, right? Like when can we extend this guy? Like when are we going to have poles? When are we not going to have poles? Okay. So we start by noticing like this guy, this W per D is different than 0 if and only if K is equal to minus nu plus 1. So in all the guys where this guy is equal to 0, then there is not even a candidate for an obstruction. So it's going to be no problem. In the case when this happens, then this guy is going to be generated. If you remember, I want a guy whose Taylor series at 0 is precisely x to the k. So how do I extend that to a shared function on the whole thing? Well, I just multiply by a function that is identically equal to 1 in an equal to the origin, and then it just falls to whatever. So I just take that guy. And then I take the integral. So I take the derivative of this guy, and I just compute the integral. As I said, I mean, like, these are like very elementary computations. A lot of stuff is, of course, going to cancel. And what I get at the end is that I need to compute this integral of this product over here. If you notice, I have an absolute value, like the absolute value x to the minus k minus 2. I have the x to the k plus 2. I just break it into two pieces, right? From minus infinity to 0, from 0 to infinity. And essentially, I have the integral of a derivative. So I will just have the value of h at 0, but coming from the left and coming from the right. And as we notice, like, we have this minus 1 to the k plus 1 that was coming from this absolute value. What does this mean? It means that when k is even, then k plus 1 is going to be odd. So then these two guys are going to cancel, and then I am okay. In the other case, I'm going to have an obstruction. My two guys do not match. And in that case, I cannot extend my distribution. So like, this is the general idea. As I said, like, this computation is, of course, like very straightforward. I mean, just an integration on R. If you have more complicated spaces, of course, like the actual computation become harder. But the idea is the same, right? You are just trying to extend your distribution for these Schwarz functions that vanish here, so you have no problem integrating and saying, okay, what happens when you have functions that do not vanish there? Well, you just break it into pieces, right? You will have your u, you have your v, you have your w, and then you break your problem. You want to understand u, you want to understand w, you want to put it together, you use homology. Okay, so let's just say, what is the answer here? Well, the solutions to these equations are going to be these guys, except when this guy is an odd integer. When this guy is an odd integer, we have seen we have an obstruction, we can no longer extend this guy. And the other ones are going to be the distributions that are supported at the origin. They are essentially derivatives of the delta function. The delta function is always there. In the case when I have a positive integer, then I have this extra guy. So if you notice, in general, I have two solutions, like one that is like this integral, and the other one that is like the delta function. And now when I have an integer, then I might have problems extending my distribution. So when it is an odd integer, I'm going to have a pole. I need to resolve my pole. And when I do that, what I get is precisely the extra distribution that I have at the origin. But actually, when k is an even integer, then I get three solutions. I have the two guys that are supported in the origin, and then the big integral, that one didn't have a problem. That one didn't have an obstruction. So in that case, I get three guys. So that's pretty much the answer. And that's how these answers kind of look like. You just check. You always want to have like some candidates of what it has to do, right? I mean, you have your meromorphic integral. You want to resolve the pole. You have a candidate, but you do not always have to resolve it. Like, sometimes you can actually extend it. Yeah. Now let's talk a little bit about like these well, the motivation from representation theory, or like from these calculations. So again, like, this is a very simple example. So I'm going to look at the group SL2R. And I'm going to look at these subgroups. So I have like this unipotent radical, I have like this Levy, I have like this other guy. And I want to look at what is called the spherical representations of SL2R. So these spherical representations are just smooth functions on G that satisfy this property. Now, for the people that is maybe like not that familiar with representation theory, what I am doing is I am taking sections on a line bundle on R, in a complex line bundle. And essentially, if I have coordinates x1, oops. Oh, I should go here. So let's say that I have coordinates x1 and y1. So this is a real coordinate. This is a complex coordinate because I have a complex vector space. And I will have coordinates x2 and y2. And what is my change of coordinates? Well, my change of coordinates is x1 is 1 over x2. And y1 is going to be y2 times the absolute value of x2 to the nu plus 1. And you have the same on the other direction. And that's the value of x1. So this is my line bundle. When I look at these spherical representations, they are just sections on this line bundle, and I have an equivariant action of my, and that's my spherical representation if you're not that familiar with them. Okay, so the action of G is just given by this formula. In this case, I just act on the right. And of course, I can look at an action on the dual of this space. What do? I just like do it this way, right? I do transpose and inverse transpose so that I still have a left action. Okay. So now I want to look at the space of n invariant linear functionals defined on this space. So essentially, I have the action of this guy, n is the 1x01. And what I notice is that if I take the derivative of that action, essentially what I have is a twisted differential operator acting on this space of sections. And I want to write down how these twisted differential operators look in this coordinate system and on that coordinate system. And then what I have to do to find these n invariant linear functionals is just solve these system of linear equations. So, okay, so I take the derivative of this guy to get my operator. So let me just run a little bit short of time. So let me just tell you what is the answer. So in local coordinates, what I do here is that I take my section and I write it in my first set of coordinates, and I get this function. And I look at this other function, and now I want to write it in the other set of coordinates. In the group representation setting, it corresponds to taking this function on the spherical principal series and evaluating these guys. Okay, so these two functions are related by this change of variables, and the reason why this is true is because this is my change of coordinates, right? So this is essentially I am just restating this part. Okay. So we remark this equation identifies this space with Nash space of sections on this Nash line bundle on the projective line. Okay. So I look at the action of n. I write this action on local coordinates. On this coordinate system, it is very nice. It's just translation. But then when I move it around, well, I have this relation between my functions, and then my action now looks very weird. It looks like that one. And now I take derivatives to get my twisted differential operators. Right, so I take derivatives, and then on this coordinate system, well, I said it was just translation. So of course the derivative is just take derivative with respect to my variable. And now I do change for variables, and I get a different differential operator, and the differential operator that I get is precisely that one that we have over there. So in other words, I have these two differential operators. I want to analyze them in the two coordinate systems, and then I want to put the solutions together. I want to glue them together. And as a remark, this operator E infinity is the transpose of the operator that we were looking before. And that was the reason why I was looking at that operator in the first place. And of course, it is the transpose because I am acting on distributions rather than on functions, right? So it really is the same problem. So we analyze the operator E0. Well, that's pretty straightforward. It's just the derivative, right? So what is the solution? The constant function 1. If I see that as a distribution, then my solution is you just take your function and you just integrate it over. Now, if you change variables and write down how that operator looks like, well, it looks like this operator that we had already seen. Right? And we have already analyzed what happens here. right? So this is precisely the gamma distribution that we analyzed in the last section. So we already know the answer to this problem. So the answer is that when my nu is a even integer, I'm going to have 3 solutions. Otherwise, I will always have 2 solutions. And some of them collapses precisely when k is an odd integer. Okay. So that's pretty much it. That's the example I was going through here. Okay. Let me talk about a very particular example, especially like the people that is a little bit familiar with representation theory. So I'm going to take this guy. So k is my maximal compact, and I'm going to look at the guy that is like constant, essentially like this constant guy. And I'm going to look at this operator. Okay. And this guy, right, when I apply this distribution to this guy, I get precisely this number. And this number has a simple pole when nu is equal to 0. What does that mean? My distribution had a pole right there, so it doesn't work. Remember, it was one of these guys where we have a problem. But according to our computations, we didn't have a problem. We were supposed to be able to extend these solutions to the whole space. So what is going on? I mean, it was supposed to be able to extend these distributions to the whole Schwarz space, but when I evaluated that particular guy, I get a pole. So that seems to be a contradiction. So the way we get around this problem is the following. So I define this new operator. So I have like this integral of my guy, and then I take the result of applying this operator to this function, but then remove it with the delta function at the origin. So outside the origin, these two guys look exactly the same. Like the only difference is at the origin. And now when I evaluate this guy at the guy that was giving problems, I get 0. Right? And for the other guys, they're going to vanish up to degree 0, which means that I can integrate them over, right? So I have moved my region of integration from nu equal to 0 to nu equals to -1. So now I can integrate. Okay. So this new operator has holomorphic continuation, like a little bit further to the left. And we see that this guy is precisely generated by this delta E and this new operator chi nu. So the point that I want to make here is that when it's very common that we have like these kernels and we say like, oh, look at these guys, I will have a meromorphic function. So I will just extend it over. If I have a pole, I resolve and then I get like all my solutions. But sometimes your distribution might have a pole, but you might still be able to fix it by saying, I'm going to modify that guy by some delta distribution, by some guys that are supported on the origin. And that way you can extend it and something that you cannot like just see by looking at the function and trying to resolve the poles. So that's the moral of like what I'm trying to say here. One thing that I want to say, if I look at this operator H, this corresponds to the matrix 1, 0, 0, -1. It will add on the delta function by this eigenvalue. On the chi nu, it acts on this other way. So when you write down the corresponding matrix, what you get is this. And then you take the limit when nu goes to 0, you get this other operator. So from the representation theory point of view, you take the spherical representation when nu is equal to 0. That guy is irreducible, which means that you should only have one intertwining operator. However, I have 2 n-invariant operators. And you can say, okay, what is going on? I am getting an extra guy? No, I am not getting an extra guy because the other guy is not an eigenvalue for H, right? So it's not going to give an intertwiner, right? It has like this 4 over there that kind of gets in the way. So that's what is happening here. Okay, I have 5 minutes left. So maybe let me just talk a little bit about invariant linear forms on this guy. I will just give a very, very brief overview of like what the problem is here, like what are the methods to solve it. I will do like no computations at all. It doesn't make any sense. I will just say that the study of these invariant linear forms on induced representations of PGL2R, it was initiated by Persson and Resnikov with a view to applications to number theory. So I think like Gordon was saying that they always want to prove like this kind of bound, right? Like you have like some functions, other functions, one says, oh, the coefficients are bounded by some guys. And if that bound holds, then good things happen. So they found some specific functions that were coming from these triple tensor products of cost forms. And they say, in this case, we can use representation theory to write down the L functions explicitly. And if I know my function explicitly, then I know the bound explicitly, and then I'm done, right? So that was the way, that was the motivation for studying these invariant trilinear forms. Okay. Later, Claire, Kobayashi, Ortiz, and Pesner analyzed the structure of the triple tensor product of induced representations for some other classical groups. Once again, here are the references. And what I want to look is, I want to look at these trilinear PGL invariant functionals on the triple tensor product of principal series representations. And maybe let me just skip over a little bit. So once again, I will have like this group that I want to look at. And I want to look at this triple tensor product of these spherical representations. So essentially like the same thing that I was doing here in SL2R, but now I have a triple tensor product. So essentially what I have is the three copies of P1, and I have a line bundle defined over there, which is just the tensor product of the line bundles on each individual guy, right? And I want to look at G invariant distributions on sections there. Okay. So in that case, I look at this guy, and the point is that I can use Frobenius reciprocity to restrict this to looking at just P invariant distributions defined only on two copies of P1. In other words, I can get rid of one of the copies and reduce the dimension of my problem by 1. And what I get is this. So let me just write here. Sorry. What I get is this guy. So you notice I get this induced representation. I have one guy, I have two guys, and I have the guy over there. So essentially, I have a line bundle defined on two copies of P1, and I just have like a twist of my action of my P. And what this is saying is that essentially I am acting by these twist differential operators, and I want to find solutions to that system of equations. Okay. Oops. Okay. So let me just tell you a little bit of how the solution looks like. So essentially, I have 3 parameters, which is nu1, nu2, and nu3. And I define these new parameters that are called alpha 1, alpha 2, alpha 3, and delta. And we define special points. Special points are where alpha 1, alpha 2, or alpha 3 are negative integers. So if 2 of these are even, then we say that we have a special point of class 1. If they are all odd, then we say that it is of class 2. And we define families of critical sets. So these are guys for which these conditions happen. So either like the alpha k and the alpha l are negative integers, or the other ones is that the alpha j has this form, mj plus 1, and the delta is equal to a negative integer. So if I have a critical point, then it will belong to one of these critical sets that I define. And the point is that if nu is a special point, right, if one satisfies one of these properties, I will show a graph in a little bit so that you can see them. Then the dimension of the space of invariant trilinear forms is 3. If it is a critical point, then it is 2. And in general, it's going to be 1. And it looks like this. So essentially, in this case, I take my parameter nu to be equals to -7/3/2. And what I have is I have these 2 lines. Over these 2 lines, the dimension of my invariant functionals is 2. And then on the red points, it is 3. On the orange points, it is also 3. Now, I want to say a little bit about like how these guys actually look like. So as I said, essentially, I'm looking at sections on 2 copies of the projective line. So I have one coordinate system on which I have these spaces. So I have the x equal to 0, I have y equal to 0, and I have y equals to x. And I have this point over here. So essentially, to compute the space of invariant distributions, I have 2 twisted differential operators that are acting here. And these operators are regular if I am outside any of these 3 lines. So in this case, I only have that solution, one solution, which is just you just integrate over the space, right, by the guy that is like pretty much translated by the elements of the groups. You just integrate over the group and you get this big guy. So that will always give you one guy. Now the problem is that you want to extend it. So first you want to add this line without the origin, this line without the origin, and then this line without the origin. Right? In that way, you will extend your distributions to pretty much everywhere except this point. And then you want to say, okay, what happens when I add this point? Right? So at every point, you are just doing like this same construction, right? Like you just analyze short functions here, then you take the quotient, and then you like analyze what happens on the open set, what happens on the quotient, and then you use homological algebra to put it together. So in general, every time that I have a distribution that is supported in any of these sets, the integral over the big set collapses. That one never survives. So it will always collapse to just a distribution supported here, here, or there. When I have distribution here and distribution there, that's going to be one of these special points. And in that case, I'm going to have my space of linear functionals to be dimension 2. I can have distribution supported here, here, and here. And those corresponds to this red point that I am seeing over there. So the blue lines are guys for which two of these guys support a distribution, and then the red point happens when the other guy also supports a distribution. But now we have like these orange guys that are like randomly appearing there. So what those guys correspond is that for some very special parameters, you are going to have two distributions that are supported just on this point, right? And that gives me like two guys. And for those guys, when you look at the connecting homomorphism from this orbit to the big orbit, you perform the calculations and it just magically happens to be equal to 0. So you get no obstructions. So at this point, like usually you only have like one distribution supported here, but at these very special parameters, you get two. And precisely when that happens, the big integral over the big orbit survives. And that's how you get like these orange points. So of course, like, I mean, at the end of it, it was very messy, but like the moral of the story is that you can try to solve this system of differential equations by looking at short functions and saying, oh, I can look at short functions over here, and then I will integrate my guys, and as long as my functions I like multiply by polynomial guys, then I will have no convergence issues. But of course, what I want to do now is extend to the other guy. How do I do it? Well, you take quotient and then you just look at power series, right? So trying to find solutions on power series is normally easier than trying to find regular solutions. And then you try to paste together your information over your open orbit and your closed orbit. You put it together using homological methods, and that way you can get the answer to your original question. And I think like that's the idea that I want to share, that this is a method that works. We've seen a couple of examples, right? And we did for SL2R. It can be done in this setting for PGL2. The computations are more complicated, and it doesn't make sense to show them here. But it is a technique that might be useful in some settings. Okay, that's all I wanted to say, I think. So thank you very much.
So you would, seems like you have nearly the machine characters and representations of the Fourier isomorphism for Schwartz class to Schwartz class. Fundamental assumption. And there is some symmetry, or is there enough symmetry? On the Fourier transform on some of these, and get the classes that Fourier maps to itself as Schwartz class.
So the question is if we can do Fourier analysis here. Is that the
Can
question?
we develop a framework? We're talking our series and some kind. Is there a dual class?
So like in this case, I mean, like the setting where I am working is on representation theory. So of course, what I'm trying to do is like break these spaces of functions like by the action of some groups, right? And this is generated in my Lie algebras. So maybe not like Fourier transforms, but what I do want to do is like break it into reducible representation, right? And look at the yeah, exactly. You just break it into the spectrum. So in this case, like essentially, like the answer will be like yes, but it will be like non-commutative harmonic analysis, right? Like that's the setting where these computations are taking place. Yep.
I think it's, so what was the results in the end for the invariant trilinear forms?
Oh, the result is that essentially they are going to look like this. So they are mostly going to be dimension 1. If it is contained in the blue lines or the green lines, then it has dimension 2. If it is in one of the red points or orange points, then it's dimension 3.
So for this subconvexity bound, that you mentioned, Bernstein and Resnick, right? You want the space to be dimension 1, or is it?
Oh, like on the example that I gave?
Yeah.
No, I mean, like, I just wanted a dimension 1 example so that the computations are easy, but I mean, like, it could be any dimension and like any space. I mean, it doesn't really matter. Like, for example, in this case, I mean, this is dimension 2, and in this case, I am taking, like, when I take connecting homomorphisms from here to here, I am going from dimension 0 to dimension 2. So the jumps can be arbitrary. It doesn't really matter.